All right, this video is about power functions, and in it we're going to answer some of these questions. How do you recognize power functions? What are its parts? How does increasing or decreasing the values in the function affect the graph of the function, affect the function itself? And how do negatives affect the functions? And what shapes of graphs do the power functions take? And where do we see power functions? Where do they appear? Okay, what are we using them for, I guess? All right, first of all, recognizing power functions. What are its parts? Well, power functions are things that look like this. I have a times x to a power. Okay, so my variable is, a power function has a variable base raised to a fixed exponent. So the x is the base, and the power b is actually the exponent. Now these are often confused with exponentials. Exponentials have a fixed base, and the variable is actually in the exponent. That's why they're called exponentials, because the variable's in the exponent. However, that's not the kind we're talking about right now. We're talking about power functions where the variable is the base. Power functions have two parameters. Okay, we have the value of a, which is the scaling factor, and we have b, which is the exponent or the power. So let's talk about how each of those affects the function. Let's talk about the effects of b first. If b is 0, then the function is going to equal the value of a. So we can see that by, if we plug in 0 for b, I would have x to the power 0, which is just 1, and then a times 1 is just a. So that means that the graph is a horizontal line through a. Okay, it's just a flat line if b is 0. Now if b is positive, then the graph is going to go through 0, 0. So we're going to have all these different power function graphs, but you can see all of them are going right here through the middle, through the origin. Okay, so we can see that by if we plug in 0 for the x, for x. If we plug in 0 for x, we have b to the 0, which is just 0, and a times 0 is 0. So if b is positive, it goes through the origin. If b is 0, it's just a flat line. And if b is negative, then the graph is going to have an asymptote. That means that the graph is never going to touch the y-axis. Okay, it's never going to touch the y-axis. Now, why would that be? That is because the denominator of a fraction can't be 0. And so, okay, first here's the graph. You can see that it's getting closer and closer and closer to the x-axis, but never touching in this direction, and closer to the y, and also never touching in the other direction. So, yeah. So now, if we look at a function, so when we have b as a negative, we have x to a negative exponent. Well, how do we make that negative exponent positive? Do you remember that we move it to the denominator? We have to take the reciprocal. So we get x in the denominator. Well, that denominator cannot be 0. And so that's why we have an asymptote. So b is negative, asymptote, positive through origin, and if b is 0, it's flat. Now the value of b also tells us if the function is even or odd. And it's just really straightforward. If b is an even number, then it's an even function, and if b is an odd number, then it's an odd function. Now let's talk about the effects of a. Okay, so let's say we have a graph here. Here's x cubed. This red line here is x cubed. The transformations that happen to this graph are the same as what we previously learned about with transformations of functions, which is to say that if a is greater than 1, then it's going to be a stretch. It's going to stretch it up higher. It's going to become narrower, like this green. So here's 10 times x cubed, and you can see that it becomes narrower. If a is a fraction between 0 and 1, then that's going to be a compression, and it becomes fatter. So it presses it down, like pressing it out here, and you can see that it became much fatter. That is the function 1 over 10 multiplied by x cubed. And then if the value of a in front is a negative, then a negative is reflection. That was going to be a reflection over the y-axis. So it's going to flip it around like that. And those would be our negative values. So that is how a affects the function. Now with power functions, here are some of the graphs of power functions. And I just want to talk about each of these graphs and some of their characteristics here. The first one here is x squared, which is quadratic. And you can see the domain is from negative infinity to positive infinity, and that the range goes from 0 on up into infinity. The graph is decreasing, 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 decreasing till 0, and then increasing after 0. And this is an even function because it is symmetrical across the y-axis. Alright, then we have x cubed. This one, it has an inflection point. So the graph is curving to the right at first, towards the right, and then it starts curving the other way. It changes directions there. So that's an inflection point in the middle. So a cubic graph. The domain and the range are both from negative infinity to infinity, and the graph is increasing the entire time. Alright, this next graph is the inverse square graph, x to the negative 2. So we can see that it has a singularity at 0, 0, which means that this is the one place on the entire x-axis that the graph never reaches. It has asymptotes on both sides from going up to infinity. The domain, therefore, is broken down into two parts, negative infinity to 0, and then from 0 to positive infinity. The range is just positive values, everything greater than 0. And again, this is an even function because it's symmetrical across the y-axis. Alright, and then we have our indirect variation. This is a graph y equals kx, indirect variation, which you guys might remember. Again, we have another singularity at 0. It's never touching that value, and the graph happens to be odd because this time we can rotate the graph 180 degrees, and upside down it would look the same. So it's an odd function. Okay. And here's the graph of 1/3, x to the 1/3. So we have x to all these different powers, right? So all these different power functions. Compare this graph to the one of x cubed. You can see that that they're inverses of each other. Okay, one is the other one simply turned, right? Okay, or reflection across the line y equals x, if you will. Great. Again, an odd function. And then I've also included the graph of x to the 2/3, so just so we have a fraction on here. So here, this point is called a cusp where the two sides of the graphs meet. And we're not going to have too many of those in the homework or anything, but I just wanted to include it so that you could see all of these different kinds of power function graphs. X to all these different powers are all things that we're talking about for this lesson. Alright, and where do we see power functions? Where do they appear? Why are they so important? Because power functions are like the little pieces that come together to make polynomials, right? Each of the pieces, x to the 5th, negative 8x cubed, 10x, and 6, each of them is a power function by themselves, and together they're making up an entire polynomial. And if we know about the power functions, we can know some things about that polynomial, such as the end behavior, which will match the power function of the first term. And those polynomials that are created from the power functions are all over the place. Stock market, water level, sound waves, curves from art. Polynomials are just really important and all over the place. And power functions are the parts that make them up. So that is our lesson.